Hi everyone, my name is Lu Xu. First of all, I would like to thank the session organizers for inviting me to present our work on ozone chemistry in wildfire plumes. This work has recently been published in Science Advances. I did the work while I was at Caltech, and now I'm working at Ceres CO Boulder and NOAA Chemical Science Laboratory. I would also like to thank all my co-authors, like NOAA and NASA, for organizing the FireX AQ campaign and for their financial support. Wildfires are a substantial but poorly quantified source of tropospheric ozone. Numerous studies have pointed out that the ozone formation in wildfires is highly variable, and an accurate simulation of ozone is challenging. In this study, by using the extensive measurements made during the FireX AQ campaign, our goals are to diagnose the key chemical variables controlling ozone formation, and to investigate the dependence of these variables on fire characteristics. The typical sampling strategy in FireX AQ, as well as other flight campaigns, is this ladder pattern, which involved multiple crosswind plume transects downwind of the fire. A widely used method to analyze such measurement is the pseudo-Lagrangian framework. Basically, the transect average or transect integrated properties are plotted as a function of smoke age to study the plume evolution, as the example shown here. However, one fundamental complication behind this framework is that many samples are not truly Lagrangian, as shown in a recent paper by Wiggins et al. In addition, the vertical transport of fire plumes also makes it challenging to track the same air mass. Because the fire emissions change dramatically over time, the pseudo-Lagrangian assumption is not valid. In fact, the change in fire emissions is often the major cause for the disagreements between model and the measurement. To address the challenge of changing fire emissions, we apply single transect analysis. This analysis examines the differences in the plume composition across each crosswind transect. The idea is that the aerosol concentration is much higher in the plume center than the edges. Aerosol attenuates the actinic flux and cause the plume center to be less chemically processed than the edges. In this example flight, the flight track is colored by OH exposure, which is estimated based on the ratio of phenol to benzene. In general, we can see the OH exposure is higher in the plume edges than the center. This left panel zooms into one transect and clearly shows higher OH exposure at the plume edge than the plume center. As a result of more extensive chemistry, the ozone, which is shown in green, is also higher in the plume edge than the center. Because a single transect samples smoke emitted at similar times, the assumption of stationary fire condition is better satisfied than pseudo-Lagrangian analysis. The results I'm going to show you are largely based on single transect analysis. If you are interested in the plume heterogeneity, presentations by Zach Decker and Sylvian Wang are highly recommended. We combine the single transect analysis with the classic scheme of ozone photochemistry. Here we define OX as the sum of ozone, NO2, PAN, nitric acid, and particle nitrate. The ingredients to produce OX include OH, VOC, and NOx. Mathematically, the instantaneous production rate of OX is the product of three terms: VOC reactivity, OH concentration, and the fraction of proxy radical that react with NO. Here the VOC reactivity is a condensed parameter describing the capability of VOC to produce ozone. It includes the VOC concentration, the reaction rate coefficient of the VOC with OH, the number of proxy radicals produced for each VOC reacted, and the alkyl nitrate branching ratio. The fraction of RO2 that reacts with NO depends on the amount of NOx. In the next few slides, I will briefly discuss how we experimentally constrain these three parameters, describe their chemical evolution, and then come back to this equation to use these variables to predict OX production. Let's start with the VOC reactivity. Roughly 80 VOCs reported in FireX AQ are classified into 7 structural categories. This pie chart shows the campaign averaged relative contribution of each category to the total VOC reactivity. On average, oxygenated VOCs, predominantly small aldehydes, are the largest contributor. The historically overlooked furans also play an important role in wildfire plumes, consistent with recent findings from the Fire Lab study. The relative importance of each VOC category to the total VOC reactivity changes with OH exposure. An example transect is shown here. Many of the prime emissions, including alkenes, furans, and oxygenated aromatics, are rapidly oxidized, and their contribution decreases with increase in OH exposure. In contrast, the contribution from small aldehydes increases over time because they have substantial secondary sources. Now move on to hydroxyradical OH. A recent study by Peng et al. Did a careful analysis on the Hawks budget using measurement from the Weekend campaign, and they found honophotolysis is the dominant OH source in the near field of wildfire plumes. Here we find similar conclusion. The left panel plots OH exposure as a function of the amount of HONO lost using the measurement of Williams flash fire. An axis value of 1 means HONO is all gone. We can see that before 90% of HONO is lost, the OH exposure correlates with the lost amount of HONO, suggesting HONO is an important source of OH. Dividing the OH exposure by the smoke age provides an estimate of OH concentration. The right panel shows the OH concentration as a function of smoke age. In the fresh smoke, there is a large variation in OH concentration. This variation reflects the difference between plume center and edges. In the plume center, where the photolysis of HONO is hindered by the low actinic flux, the HONO concentration is high as indicated by red, but the OH concentration is low. It's the opposite trend in plume edge. As smoke ages, HONO is depleted throughout the plume. The difference between plume center and plume edge gradually diminishes, and the OH concentration reaches background level. The last variable I want to discuss is the fraction of RO2 that reacts with NO. Ozone is produced from the reaction of RO2 with NO. Other RO2 reactions do not produce ozone. Therefore, knowing the RO2 fate is critical to understand OX formation. With direct measurement of oxidation products from different RO2 reaction pathways, we are able to provide the first experimental constraint on RO2 fate in wildfire plumes. To illustrate, this figure shows the evolution of propane-derived peroxide and hydroxynitrate in two transects with different NO levels. Peroxide is from the RO2 reaction with HO2, and hydroxynitrate is from the reaction of RO2NO. The left panel shows a high NOx transect, where the NO concentration shown in black and the right y-axis is above 500 ppt. Under this condition, only hydroxynitrate shown in blue is produced, and hydroxynitrate is a product from RO2NO reaction. The right panel shows a low NOx transect, where the NO concentration is below 500 ppt and reach as low as 50 ppt. As a result of this low NO, both peroxide and hydroxynitrate are produced, suggesting the RO2-HO2 and RO2-NO reactions are competitive. Therefore, by using the production of peroxide and hydroxynitrates, we can calculate the fraction of RO2 that reacts with NO for each transect using this equation. This slide compares the evolution of RO2 fate for the Williams flash fire sampled on 2 different days. On both days, the fraction decreases with increasing downwind distance, illustrating a transition of RO2 fate from an RO2NO dominant regime to a mixed regime with increased importance of RO2-HO2 reaction. This plot also shows that the transition rate varies between fires. The transition is slower on August 7th, shown by the stars, than August 3rd, shown by the circles. Such difference is likely caused by the fire strength and the fuel consumption. The fire on August 7th has a fire radiative power FRP up to 4 times 10 to the 4th megawatts. Larger FRP indicates more fuel consumption. As shown by the color bar, the FRP on August 7th is much larger than that on August 3rd. It makes sense that the transition in AO2 fate is slower in larger fires, because it takes more time for the NOx concentration to decline to a level where AO2-HO2 reactions can become competitive. What I want to emphasize is that over 90% of fires around the world have FRP smaller than 100 megawatts, which is here in the color bar, meaning that the transition of AO2 fate in majority of fires occurs really quickly near the fire. The implication of the fast transition of AO2 fate is that a large fraction of wildfire VOCs is oxidized in the mix regime. For example, for both fires, when the AO2 fate transitions into this mix regime, roughly 70% of the VOC reactivity remains. The change in AO2 fate is a result of NOx decrease. We did a comprehensive analysis on the NOI budget, the evolution of NOI species, and the relationship between NOI species and the fire conditions. But limited by time, I will not go into all the details. Now, we return to the conceptual model to test the chemical closure of OX in wildfire plumes. Integrating this equation from the fresh to the aged portion across each plume transect reflects the predicted OX formation based on the measured VOC reactivity, OH exposure, and AO2 chemistry. Then, the predicted OX production can be compared to the directly measured OX production of the same transect. This plot shows the comparison result. The y-axis is the predicted OX production from VOC decay, and the x-axis is the measured OX production. Each data point represents one transect for which the OX production and AO2 fate can be quantified with high confidence. Overall, the predicted and measured OX production agree within 10%. Such agreement suggests that the majority of VOCs contributing to OX formation have been quantified during 5x AGU, and there are no apparent missing sources or sinks of OX. As discussed above, the ozone chemistry undergoes rapid transition in chemical regime. So how to simulate this? Instead of pushing the spatial resolution and chemical complexity in atmospheric models, we propose to parameterize the near-field plume evolution. Here we switch the target of investigation from OX to the sum of ozone and NO2 because they are criteria pollutants. By applying a stepwise multivariate regression model, we find that the production of ozone and NO2 can be reasonably predicted based on MCE and OH exposure using this expression. The term in the red box represents the ozone and NO2 formation during plume aging. The field data indeed shows a significant correlation between OH exposure and the production of ozone and NO2, as shown here. The other two terms in the blue box represents the MCE-dependent emission ratio of NO2. To examine this parameterization, we compare the field-derived emission ratio of NO2 to that measured in the fire lab study. In the right bottom plot, the heat map represents a compilation of emission ratio of NO2 from 10 different types of biomass burned in the fire lab, and the line represents the field-derived parameterization. We can see the empirical parameterization reasonably agrees with lab measurement. So overall, this field-derived parameterization is a good approximation of the subgrid scale ozone and NO2 production for atmospheric models without an accurate emission inventory and fuel characteristics. To summarize, wildfires emit HONO, NOx, and an enormous diversity of VOCs. In the near field, OH produced from the HONO photolysis initiates the VOC oxidation, which proceeds in the presence of NOx and leads to efficient ozone formation. After a few hours, the plumes run out of HONO and NOx. Fewer AO2 react with NO, and the ozone chemistry slows down. But the VOC remains elevated. Therefore, when these fire plumes mix into urban atmosphere reaching NOx, ozone formation will begin again and impact the air quality of the city. With that, I want to thank you for your attention. Here lists my contact information, and feel free to reach out to me if you have any questions or comments.